Minimizing misclassification rate. In the previous lecture on decision theory, we ended the discussion saying that in order to make the decision, we had two different methods. One is minimizing misclassification rate, and the other one is minimizing expected loss. So we'll look into both these approaches separately. Here, let us see into the first approach, that is minimizing misclassification rate. How will this approach help us to make a decision? So let us make the aim clear initially. That is, our aim is that whatever classes we have to assign our input variable to, we have to make sure that maximum of those gets assigned to the right class. Let's say we have two classes C1 and C2. We have an input variable X. So whatever be a new value of X that you get, it should be rightly assigned to C1 or C2, right? So we'll take the same example that we used in the previous lecture. Input variable is X. Here is the problem statement that let's say this is the border of a country and you have put a lot of security cameras here in the border. These are all security cameras. These will be looking into any approaching enemy all the time. Let us say this camera found few people approaching. There are few people approaching. The task is to find whether these are enemies or are they civilians. So in case it is detected as enemy, you want to send troops to this location in order to protect, right? So the task is to identify whether it is an enemy or not. If it is an enemy, so that is the first part. Identifying whether it is an enemy or not, that is the first part by finding probabilities. Once you find that part, the part of making decision, what is the decision that you have to make, whether to send troops or not, this is the decision. And our first approach in making decision is minimizing misclassification rate. That is, while you are classifying into enemy or not, this decision should be made such that misclassification is the minimum. This is the decision approach that we are using. Let us see how this works. Okay, then you will understand clearly. Let us say the X be the input variable, that is from the camera we are seeing these people, and from this we are taking certain information which will pass to our machine learning model. So let the information include the dressing that these people are having, let's say item in hand, items that the people are having in their hands, then the bag in their shoulders, and let's say their body language. So these are the same criteria that we chose in the previous lecture so that you can relate these things. Okay. And what is the target? Target T. What is the target? It is presence of enemy, right? Presence of enemy. You have to identify either there is a presence of enemy or if there is not. This is your target. This is your X. Using this X, you want to reach this target. Either you have to say there is a presence of enemy or you have to say no enemy. Okay. So we did put it into two classes, C1 and C2. C1 said it is an enemy, right? And what is C2? Not an enemy, right? So these were our two classes. So our idea is that we should be able to assign it to either the class C1 which says it is an enemy or the class C2 which says it is not enemy, by making sure that misclassification rate is the minimal. This is our final aim. For this particular approach, this is our aim. We'll see a different aim in the minimizing expected loss approach. Okay. So what is our goal? What is your goal? Goal is to make as few misclassifications as possible. And the decision rule that you will use, that is to assign X into one of the classes, C1 and C2. This is what you are going to do. The first thing we'll do is that when you assign, I'm removing these parts. When you assign it into C1 and C2, what you are doing, you are in effect dividing your input space. Let us say this is your input space from where you are choosing X. This input space, you are dividing it into two regions. One region is R1 and the other is R2. So this R1 belongs to all those input points. So this is the input space of X. Okay. All this includes X, different values of X here. And you are dividing it into two regions now. That is your machine learning model. What it is supposed to do is that it want to divide this input space into two regions. First region is R1, this is R1. Second region is R2, this is R2. In R1, whatever points are there in R1, they are all supposed to be classified to class C1. And whatever are there in R2, they are all supposed to be classified to C2. One thing, just to make it clear to you, I drew a line right in the middle just by dividing it into two particular portions for easiness and for easier understanding. In reality, when a machine learning model does this, what will happen? There will be a lot of regions inside. That is, if this is your total X space, here there will be many regions. There will be many regions which need not even be connected. There can be many other regions, and see, many of these regions will be part of R1. This will be R1, this will be R1, this will be R1, and maybe this is R2, this is R2, and so on. Okay. So your whole region will be divided into R1 and R2. Doesn't mean it need to be continuous or together or something. I am drawing it together so that it will be easier to explain and also for you to understand. So this is R1, this is R2. What is this called? This is called your decision boundary. Whatever is the line that you've drawn right in the middle in order to differentiate between R1 and R2. This is your decision boundary. So ultimately your model will be identifying this decision boundary so that whichever points are on the R1 side, it will be classified to class C1, and whichever points are there in the R2 side, they will be classified to class C2. Why am I calling it points? Because whatever be your input data, it may have multiple components. They totally contribute to one point. That is for understanding. Okay, you can consider it as a 4-dimensional point here because there are 4 different attributes. Now, the boundary, you understood the concept of boundary, decision boundary. What is a mistake? I'll rub this off. When will you commit a mistake? When will you commit a mistake? Either when input vector is belonging to class C1. Let's say actually it is class C1, but what did you do? You assigned it to class C2. This is a mistake, right? Similarly, if it is actually belonging to C2, but you assigned it to C1, both these are the two types of mistakes you can commit while doing this particular classification. And what is your aim? To minimize misclassification, that is to minimize the mistake. You want to minimize these type of mistakes and also this type of mistakes. This is your ultimate aim. So in order to do that, what do you have to do first? You have to find the probability of committing this mistake, and then you have to decrease that probability. That's how you can deal with it, right? So how can you write that probability? That is the chances of your identifying a C1 point as C2 or C2 point as C1. This is the mistake. Let's say probability of mistake. How will you write this? Probability of X belonging to R1 and assigned classes C2. Right? This is one possibility. That is if X is actually belonging to R1, but you assigned it to C2, which means it is a mistake. And what is the second type of mistake possible? That is when X belongs to R2, right? X belongs to R2 and you assigned it to C1. These are the two types of mistakes. Why am I writing like this? P of X C formula. I'm writing this because what does this mean? The joint probability of X and CK happening together. That is X belonging to R2 and classification into C1, both happening together. Whatever is the probability of that, that is the probability of mistake, right? Understood? How can I express this? If it is, I'm considering it as continuous variable, then I will integrate over the range R1. Why? Because whatever values of X are there in the region R1, that is what I have to identify. So I'll integrate over the region R1, P of X C2 dx. Okay, this corresponds to this term. That is over the region R1 I am integrating, which means I am considering all those points which actually belong to R1 and I am saying if I assigned it to C2, that is a mistake. Plus, what is the other kind of mistake? Integrate over all R2 P of X C1 dx, right? This is the case in which point actually belongs to region R2 and I am assigning it into C1. So what is R1 and R2? R1 is the region where it is supposed to be in C1, but here I am assigning to C2, which is a mistake. Similarly here also. So this is what you have to minimize. Till this point it is clear. Next thing that you have to think is, if you want to minimize this whole thing, what should you do? You want to minimize this whole integral. So what should you do? You have to assign x to whichever class which has the smaller value of the integrand. That is, if the integrand increases, your error is increasing. Probability of mistake is increasing. So what will you do? You will assign it into that particular class which has smaller value of integrand. When will it have smaller value of integrand? When p of xc1, let's say, if this is greater than p of xc2. Now you know that the value p of x and c1 together, that is the chances of this x being put into c1 is greater when compared to xc2. In this case, what should you do? You should assign into c1, because then you have lesser chances of causing a problem, right? So in this case, what do you want to do? If p of xc1 is greater than p of xc2, then you will assign it into into c1 class. So let us understand this by taking generalization. Let's say p of xck. So k is the class here, okay? How do you find this? In order to find this, you will do it like this: p of ck given x into p of x, right? This we had learned in the previous classes how this comes using product rule. So p of x ck is p of ck given x into p of x. That is, here given the data x, what is the probability that it belongs to class ck. Here p of x, what is the speciality of this term? This is common in all the cases. That is, if you use this formula for C1, C2 or whichever class. Here we are considering k different classes. That is why I took CK. So C1, C2, whichever be the class, you substitute that here. This P of X term is common. That is, when you're comparing between the case of C1 and C2, P of X term becomes irrelevant because this term is present in both C1 and C2 case. So there is no point in taking this into consideration in order to understand which one is higher. So if you remove this P of X term, what remains? P of Ck given X, which means your final rule is to assign it to whichever class which has higher value of P of Ck given X. And what is your P of Ck given X? From the lectures till now, you understood this is posterior. So finally, in order to minimize the misclassification rate, what do you have to do? You have to find the posterior and assign this point to the class which has higher posterior probability. That is P of Ck given X, posterior. Whichever has higher posterior, you have to assign it to that. So till this point it is clear. I'll show the same thing from a different way of solving this. That is, here what we did, we found whatever is the chances of a mistake, we tried to minimize that mistake. What is the other way of dealing with this? You can maximize the chances of success. That's the other way. That is, instead of minimizing mistake, you can maximize success. And my point is, when you do that solution, that should also end up in the same answer. Then whatever we are doing is right, because whether you minimize mistake or you maximize success, both should take you to the same answer, which says you have to increase the posterior P of Ck given X, right? So let us see that approach. Instead of minimizing mistake, what I'm going to do, I'm going to increase the probability of it being correct. Probability of correct. I'm increasing the probability of it being assigned to the correct class. When will it be assigned to the correct class? When P of X element of Rk and Ck. This happens. That is, here I had considered R1 and C2. That is wrong class. Here I am considering right class. That is, region K is assigned to Ck, which means right assignment. And this I have to do over all the case for all the classes. Here we consider just two classes. Let us say there are K classes. Then sum over all the classes k equal to 1 to k over all the k classes. If you do this, this total probability you want to increase, right? And what is this? This is equal to sigma k equal to 1 to k. And what is this probability of x element of Rk Ck? It can be written as integral over the region k p of x Ck dx, right? The same way you wrote all these things. So finally it boils down to you have to sum over all the regions k. For that region k, take the integral over that region of p of x ck dx. And what do you want to do? You want to maximize this value, increase this value, right? I'll rub this off. And this is up to k. Okay, so this time your aim is to increase this value. That is, minimizing misclassification means increasing the right classification. So this is you have to increase this particular probability. When can you increase this particular probability? When p of x ck, this value increases, right? So p of x ck, this value has to increase. What is this? This is p of ck given x into p of x. This is what you have to increase. And this takes you to the same solution that you previously saw. That is, you have to increase p of ck given x. What is this? Your posterior. You have to increase your posterior in order to minimize the misclassification rate. So in order to make the decision, that is, you found the probability, and finally you have to make the decision, that is, what is the next action to be taken. In order to take the next action, there were two approaches. One is minimizing misclassification rate, other one is minimizing expected loss. So in this lecture we saw the minimizing misclassification rate approach, in which in order to make the decision, our criteria is that we want to minimize the chances of it being assigned to the wrong class. And by that approach we understood that the approach we should take is to increase the posterior. Whenever you get any point which you want to assign to the right class ck, what would you do? You'll take that data x and then you will find the posterior probability of ck given x for each of the class. Whichever class has the highest probability of ck given x, that is, for c1 you will find p of c1 given x. Similarly, for c2 you will find p of c2 given x. Then you will see whichever class has the higher posterior, and whichever has the higher posterior you will assign it into that class. So this is how you make the decision in minimizing misclassification rate approach.